All right, let's imagine that we're all on a school bus, okay? And we are speeding up. We all feel pushed back into our seats. We're actually accelerating forward, but we feel like we're being pushed backwards. We always feel like the way we feel is the opposite of the direction that we're accelerating. So if the driver slams on the brakes, then we'll all feel like we're going to fly forward, and we're actually accelerating in the backwards direction. If you're going around a curve, okay, you may feel like you're getting pushed towards the outside, okay? The acceleration is actually going towards the inside. So whatever way you're feeling, you're actually accelerating in the opposite direction. An acceleration, that is simply a change in your velocity. So we're going to review speed and velocity here. Speed does not have a direction. Velocity does have a direction. Velocity, therefore, is a vector, and speed, therefore, is a scalar, because vectors include a direction, scalars do not. But they both tell us how fast we're going, okay? Acceleration is a change in velocity. So if we change any of the things over here, then we will be accelerating. So if we change our speed by going faster, we are accelerating. If we change our speed by going slower, we are accelerating, or we can change the direction to accelerate. So on your notes, it should say acceleration is a change in velocity. And in the next line down, that means you could be speeding up or slowing down or changing direction. If you need time to write all of those down, press pause and then continue when you're ready. Oh, there we go. Just sped off to the side. So it sped up and it changed direction. So it was accelerating there. Okay, so for acceleration, we need to distinguish between a beginning condition and an ending condition. So you need to change your velocity. So you have to have your beginning velocity, and then you need also an ending velocity. I don't know why. There we go. Yeesh. They all came at once, sorry. So in our example here, the beginning condition, we call that V1, the first velocity. So a sprinter runs the first 5 meters of a 100-meter race at 3 meters per second. That is our first velocity. An ending condition, that is at the velocity at the end. Okay, so let's see what they say. A sprinter runs the last 5 meters of a 100-meter race at 12 meters per second. So they accelerated, they changed their speed. In this case, they sped up. They went from 3, that's the beginning condition, to 12, that's the ending condition. So on your paper, where it says V1, you should write 3 meters per second. Where it says V2, you should write 12 meters per second. We're in the first box, okay? So we got the same question here. A sprinter runs, okay? So that's where we are. We've got V1, 3, V2, 12. The whole race takes 9.4 seconds, so that is our time. What is the racer's acceleration? Okay, so first we have our equation. It's a circle equation again. So A and T are on the bottom of the circle, and V2 minus V1 is at the top of the circle. So in this case, if we cover up the A, it says equals V2 minus V1. So here we go. If you missed it before, here's our variable menu for the same stuff we were just doing. So V1 is 3, V2 is 12, and the time is 9.4 seconds. We're trying to find A. Our equation, A equals V2 minus V1 divided by T. Then we're going to substitute our numbers in. So let's see, we got V2 is 12, V1 is 3, and the time is 9.4. You need to subtract first. You need to do the whole top. So 12 minus 3 is 9, and then 9 divided by 9.4 gets me 0.96. And the units for acceleration are a distance over a time squared. So it's meters per second and then per another second. So we put squared in the bottom. All right. Acceleration is a vector. So we've got this sprinter here. Oh, there we go. So they're speeding up. So they went from the 3 to the 12. So they went somewhere in between. They were going 4.2, 6.5, 8.4. So here we go. What about a baseball player sliding into home? What would their acceleration look like? It will be a little bit different. They're slowing down. So from 12 to 10 to 6.5 to 3.7 to 1.2 and then to 0 when they come to a stop. And then we could change direction as well, but we're going to get to that in another chapter. All of that is your acceleration. This case, the acceleration went the opposite way they're moving. So the acceleration would actually be negative in this example. All right, not quite time for homework, but we're going to go ahead and try the problem. So on your problem, you've got 15 for V1, 40 for V2. We're trying to find A, and the time is 50 seconds. So we've got our equation. We need to substitute in and solve. You should get 0.5 meters per second squared. And then we've got another practice problem. A roller coaster increases its speed from 0 to 100 in 10 seconds. Our first speed is going to be 0. Our second one is going to be 100. And our time is 10. So we have 100 minus 0 is 100. 100 divided by 10 is 10. So we get 10 meters per second squared. All right, one more practice. It takes 100 kilometers per hour train 15 minutes to slow to a stop at the station. All right, this one's a little tricky because you have to convert minutes into hours. 15 minutes is a quarter of an hour, which is 0.25. If you get negative 400 kilometers per hour squared, great. If not, we'll try that one together in class. So make sure in your notes here you have your work shown, okay, not just the answer. The answers are here so you can kind of check it. But make sure you substitute everything in and filled it out so that when I look at it, I can see that it is all there.